Can I get a new set, please? Yay! Can I get a new set, please? When I say something like 27 times 11, so this one would be 10608. 11024. That's a fun one. 12100. That one's a little tricky, isn't it? 10712. What's going on here, right? So finally, as promised, oh, hey, welcome to your Monday Math Minute. My name is Tim Ricchuiti, and I'm going to guide you over the next guaranteed no more than 10 minutes, and guaranteed to be here on Monday. I'm going to guide you over how to answer a bunch of these questions. So first of all, let's see how quickly I can do them. 11227. Okay. So I think it's finally time for us to really dive in and figure out what's going on using double distribution or the area model, same thing. Gosh, I'm kind of all over the place today. So why do I keep calling this area model for multiplication double distribution? One way to approach it is to do what we did the other day. 27 times 11 is the same thing as 27 times 10 plus 1. And this would be considered a single distribution, right? Because I'm only distributing to one term. But another way to consider it, and this is what we were looking at last week, is that I'm going to do 20 plus 7 times 10 plus 1. Something called FOIL. First, outside, inside, last. The idea is, okay, first we multiply the 20 times the 10 when we have things that look like this with parentheses. And then we multiply the outsides and the insides, and then we multiply the last part. So 20 times 10 plus outsides 20 times 1 plus insides 7 times 10 plus last 7 times 1. And of course we get 200 plus 20 plus 70 plus 7, or once we add everything together, 297. Now, if you ever did anything like this, you probably didn't do it for numbers. You probably did it for these things called polynomials, where you multiply out something like x plus 7 times x plus 1. And again, when you do your first, outside, inside, last, you end up with first x times x plus outside x times 1 plus inside 7 times x plus last 7, I guess I should write 7 times 1. And in this case, we end up with x squared plus x plus 7x plus 7, or what we more frequently write as x squared plus 8x plus 7. And that's fine. There's nothing wrong with FOIL, or as I call it, double distribution. You can see we're distributing the 7 once, and then we're also distributing, of course, the x once. And so that's why I'm calling this double distribution. But the area model for multiplication is, no worse, certainly, just as good, and it just gives us a different way to visualize what's happening here. The x times the x is x squared. X times the 7, 7x. X times the 1 is x. 7 times 1 is 7. What we would typically see in this scenario are like terms along that diagonal. And of course, you'll note when we add everything together, we end up with x squared plus 8x plus 7. So that's why I keep calling this double distribution. And again, it works whether you're doing polynomial multiplication, which is what I just did here. It involves variables, or whether you're just doing actual multiplication. Just to give one final example with some two-digit numbers, 27 is 20 plus 7, 11 is 10 plus 1, and as we multiply all of that out, 20 times 10 is 200, 7 times 10, 70, 20 times 1, 20, and 1 times 7, 7. And we end up with our product, 297. Why does this matter? Why do we care? I'm trying to show you how to multiply out things like 107 times 104 is a great example. So let's think of, and I would call this the numbers just above 100 trick. Let's think of 107 and 104 as 100 plus 7 and 100 plus 4. When we do our multiplication now, 100 times 100, of course, is always going to be 10,000. if we're doing these numbers just above 100. 7 times 100 will be 700, 4 times 100, 400, and then this box ends up being the product of 7 and 4, which is 28. As I showed you last week, when we line all these up, something interesting ends up happening. The product, that is this thing right here, always comes down in at least 2 digits. Sometimes more if we need a carry. I'll show an example with a carry in a second. But if we're just doing numbers slightly above 100, we wouldn't often have to carry. And then these next two boxes, you would do the 0 plus the 7 plus the 4 and a carry, right? There would be a carry involved. But you'll note ultimately what we end up with is simply the sum. How many hundreds? 1100. So first we ended up with a product at the end. 4 times 7 is 28. And then we ended up with a sum. 7 plus 4 is 11. And of course, because we are doing the numbers just slightly above 100, we're going to get numbers relatively close to 10,000. And so that's what that initial one is doing there. And that's how we know this ends up being 11,128. Let's put that to practice again. All right, 105 times 106. Now the point eventually is not to do the box, but to do this in our head. But just so you can see one more time, we can think of this as 100 plus 5 and 100 plus 6. This box here will be the product. 5 times 6 is 30. Of course, 100 times 100 always going to give us the 10,000. And then these two boxes here, plus 500 plus 600. And when we write all this out, we see again this distinctive pattern emerge. We've got carrying down to our ones places and our tens place simply the product of 30. We've got coming down to the thousands and hundreds place what ends up being the sum. 5 plus 6 is 11. And of course we know that we're always going to get that number just above 10,000 because we're multiplying numbers just above 100. 100 times 100 is 10,000. And so we end up with 11,130. So let's see now how many of these we can do, but this time I don't want to write the box down. I just want to write down the product. So again, we're doing mental math. We're taking advantage of the area model for multiplication, but we want to move away from the model and start using a heuristic, a trick essentially. 105 times 102, numbers just above 100. I'm going to take how far above 100 they are, and I'm going to add that together. In fact, one way you can think about it is just take this number here and add it to your 105. 105 plus the 2, how much bigger that second number is than 100, is 107. And then we want to take the product of how much bigger each of these is than 100. 5 times 2 is 10. So the answer here is 10,710. 103 times 111. So we add the 11 to the 103, and we get 114. And then we're going to do the 3 times the 11, and we get 33. So that one ends up being 11,433. Perhaps at this point we're all getting a little faster. We're ready to move a little bit more quickly. 104 times 106. I add together. 4 times 6 is 24. 11,024. Ooh, now what do we do if we have a carry? You might think, okay, so let's just keep doing the same thing. But then 14 times 11, if I'm using a different trick in my head, I know that's 154. And how am I supposed to write 154? Clearly this isn't 125,154. So what's going on here? Well, this is one where we end up having to carry. In fact, if you were to write this one out, so if we do go back to the actual box method to see what's going on here, we have 100 plus 14 and 100 plus 11. And that gives us products of 10,000, of course. The 154 I mentioned a moment ago, 11 times 14 is 154. And then we have 1,400 and 1,100. So when we write all these out, you'll notice the only thing that ends up being different is that the product here in this box was a 3-digit number instead of a 2-digit number. And essentially what that's going to end up looking like is a carry. The 54 still comes down, but now when I do the 11 plus the 14, I get 25 plus the 1 makes 26, and then I bring down that 1, and so there's my answer. Not 125, 12654. Now again, this doesn't happen a lot. In fact, looking through my list, the next time I see it happening is really here, 112 times 110. And so sometimes it's better to start with the product. What's 12 times 10? It's 120, but I'm going to keep that 1 in my head as a carry. What's 10 plus 12, or plus 112, 122, plus the 1 carry, 123. And so that's going to be 12,320. A few more of these just to finish up with 10812. Did you beat me yet? What's 106 times 106? Product is 36. Sum is 112. What's 104 times 115? Product is 60. Sum is 19, or 119. So hopefully you're getting the hang of it. Maybe this one today is going to be a little bit shorter. We'll see. That is your Monday Math Minute. Guaranteed to be on Monday. Guaranteed to be no more than 10 minutes long. Have a good day.